If you throw an object, it inherently wants to keep moving in a perfectly straight line forever. That is Newton's first law of inertia. To force that object to abandon its straight path, to bend its trajectory into a circle, requires a constant physical pull toward the center. Physicists call this requirement centripetal force. It functions as a job description. Something in the physical environment must step up and provide that inward pull. Take a stone tied to a string and swung in a circle. The string yanks the stone toward the center, meaning the tension in the string is performing the job of centripetal force. This diagram shows the exact mathematical demand for that pull. The required force, labeled here as Fc, is the product of the object's mass and its velocity squared, divided by the radius of the turn. If the physical world cannot provide a tether to satisfy that equation, the circular motion fails. The object immediately breaks free and travels in a straight line. Consider a car taking a sharp turn on a perfectly flat road. There are no strings attached, yet the car turns. We have to identify the specific force acting as the tether. Gravity pulls the car down, and the road pushes back up with normal force. They perfectly cancel out. Thus, the only inward horizontal force is static friction. But friction has a strict limit. As speed increases, the rubber eventually fails. This creates a hard speed limit for any flat turn. We calculate it as the square root of the friction coefficient, the radius, and the pull of gravity. On a flat road, safety depends entirely on the grip of the tires. If the driver exceeds that friction limit, the invisible tether snaps and the car slides off the track. To solve this problem, engineers override the physical limits of rubber by altering the geometry of the road itself. On a tilted track, gravity pulls straight down. But the normal force, the road pushing back, is always perpendicular to the surface, tilting inward. We resolve this tilted force into two components, one fighting gravity and one pointing directly toward the center. The road itself now provides a horizontal push. The inward component of the road's surface teams up with friction to help keep the car on its path. By banking the curve, engineers use the weight of the vehicle against the slanted surface to push the car through the turn. This teamwork between the tilted road and the tires significantly increases the maximum speed a car can handle before slipping. This raises a question. If we removed friction entirely, say by covering the track in ice, could the car still make the turn? At one specific speed, the inward push from the banked road alone provides the required centripetal force. Here, the friction variable drops out of the math entirely, leaving the formula for optimum speed, depending only on gravity, radius, and bank angle. Driving at this exact speed prevents lateral wear on the tires. Because the road's geometry does the work, the car rolls without sideways sliding. Circular motion is achieved through the precise manipulation of these vector forces. By tilting the track, engineers ensure that even at high speeds, a vehicle stays on course, guided by the shape of the road itself.